Today, we're going to continue looking at linear functions, which are patterns of repeated addition. The things that we want to remember from this class is that I advertise multiplication as repeated addition. So multiplication has to come up at some point when we're talking about a pattern of repeated addition. I also mentioned that we're talking about linear functions. One of the things that might come up for us from our past in linear functions is y equals mx plus b. Even if you don't remember y equals mx plus b from some linear functions from before, it's common enough that I'll just bring it up. Y equals mx plus b. But what we want is to be able to read what that expression is telling us. And I think it reads better if we start with the fixed value b and add mx. Because then we can read this expression by saying we start at b and add m a bunch of times. We're doing the repeated operation of adding m, and there's the multiplication, m times x. X is the a bunch of times. X is the steps, the number of steps that we're taking. M is the abbreviation that we use for the slope, and we want to remember that slope is rise over run. Rise is how y is changing. Run is how often y makes that change. So we could usually describe that as change in y divided by change in x. These are the more common searchable things as far as slope goes. So we want to look at an example, and we want to recognize that the slope is a ratio. So the slope is proportional. Let's take a look at an example. So here we have a function. I got 3 lines in my table. The variables that are in play are x and y. We have x inputs and y outputs. And we can see from the x and y what's going on in this function. We can write a sentence to describe what's going on. We have an x equals 0, so we'll say that's our starting value. We'll say y is 17 when x is 0. And it looks like y is increasing by 4 every 3 units. And y is increasing by 4 every 3 units. So here are the 3 things that we need to describe a linear function. Where y starts, how y is changing, and how often we make that change. And these are we're just quantifying what we mean when we say it's increasing by 4 every step. So each step of the way. The adjustment that we're making now is that each step is 3 units. So the step size is 3 units. The normal way we would think about this function, the normal y equals mx plus b way we would write an equation for this function is we would identify the start as the y-intercept. Good thing that we have x equals 0 to go along with that. Where when we say y increases by 4 every 3 units, we're saying that the rise is a positive 4, and this happens every 3 units, so the run is 3. So we can combine these to make a slope where we take the rise of positive 4 and divide by the run of 3. So our slope is 4/3. So the equation that we could write for this function, we could say y equals, we'll start off at 17 and add 4 every 3 units And then we add 4/3 a bunch of times. Here's the a bunch of times. We multiply by x. What we want to recognize is that the slope is a ratio. And we usually go for the simplified form, 4/3. But there are many ratios that are equal to 4/3. I can have 8/6. But if we look at the table, that is also happening. 17 plus 8 is 25, and 0 plus 6 is 6. We can also think of this at 8/6 as 12/9. Because if we go from 17 to 29, that's 12, an increase of 12, divided by 3 increases of 3, which is 9. Or if we go from 13 to 25, that's an increase of 12, and from -3 to 6 is an increase of 9. We can also even go the other direction. We could think of a positive 4/3 as -4 over a -3. So we can see from 17 to 13, that's a decrease of 4, but that would be 3 units backwards, or a -1 step. So we usually list the slope as a ratio of rise to run because we can. But when we write it this way, we end up with an alternate description of what's going on in the function. So when we put the 3 underneath the 4, we're thinking of what's going on is y equals 17 when x equals 0. And we're looking at what happens every 1 unit. So we'll say, and y is increasing by 4/3 every 1 unit. So this might make us come up with a different table entirely. But that different table would just be the in between the 0, the 3, the 6, and the 9. So if I start off that, if I look at that table, we could start off at 0, 17. And now we'll increase by 4/3. 4/3 is 1 1/3. So let's remind ourselves of what's going on here. So I'm going to increase by 1 1/3 every 1 unit. So we just have to practice counting by fractions. Well, not in x. X is nice and simple. 1. But 17 plus 1 1/3 is going to be 18 1/3. Then if I add 1 1/3 again, when x increases by 1. When x is 2, 18 1/3 plus 1 1/3 is going to be 19 2/3. And then when x increases again by 1, this should match up what we had in the table for x equals 3. So we should be at 21. So 19 2/3 plus 1 1/3 is going to be 20 3/3. But 20 plus 3/3 is 20 plus 1, or 21. So it matches up with what we had. We're just looking at it with smaller steps. So what we want to do today is look at these steps, the steps that are 3 units long. Because what I want to say start at 17 and add 4 every step. let's see explicitly where we can see those steps. And then I'll explain why I want us to look at the steps in that, the steps in the way that I want to look at them. I was hoping there was a sentence in there somewhere. So I've got this equation, y is equal to, start off at 17 and add 4 every 3 units. And we multiply by x because that's the number of units. What I want to do is represent the number of steps. I want the x to, I want the plus 4 to be multiplied by the size of the step, or by the number of steps. I want this to look like y equals start plus the change in y times the number of steps. So to write this as the start plus the change in y times the number of steps, all we need to do is take the divided by 3 parts and move it under the x instead of the 4. So we have 4 divided by 3 times x. This is all just a bunch of multiplication. I can write it as 4 times x and divide by 3 if I want. This is not going to change how anything functions, how any of the numbers function. It's not going to change anything with regards to the order of operations. It's just going to change how we're thinking about what's going on. So instead of writing it as 4/3 x, the usual way we summarize the slope, I'm going to write y equals, start off at 17 and add 4 a bunch of times. And the bunch of times is going to be x divided by the step size. Because if I just take the number of steps, I can write the number of steps as x divided by the step size. The number of steps that we're taking is x divided by the step size. So that's why that first table looked like start at 17 and add 4 a bunch of times. Add 4 every step. But to make every step size of 3, we can write this as x divided by 3. This would be a very strange way to write a linear function. So, admittedly, this is a strange way to write a linear function. And indeed, this is not how I would want you to write a linear function. If you get out of this class and start writing your linear functions this way, people are going to think you're strange. So I guess if you want people to think you're strange in the way that you write your linear functions, go ahead and write them this way. This is not about how I want you to write linear functions. This is a strange way to write a linear function, but this is exactly how I want you to think linear functions. I want you to identify the step size and imagine taking the x and dividing it by the step size, so that when we're multiplying by 4, that is counting the number of steps. So in our table of values, I had that one row for the number of steps, and I had the other row for the x. When x is 0, we've taken 0 steps, but when x is 3, we've taken 1 step, and when x is 6, we've taken 2 steps, and when x is 9, we've taken 3 steps. Notice that the number of steps is just x divided by the 3, which is the step size. So we start off at 17 and we add 4, and we add 4, and we add 4. We only add 4 at full multiples of 3. The step size is 3. Here are the number of times we've added 4. That's counting the number of times we've done the plus 4. Here is why I want us to think of linear functions in this way. I want you to think in terms of step size. The reason that we write slope, write y equals mx plus b and summarize the change in y and the change in x by just dividing those two things is because we get all this stuff that's multiplied together. Changing the step size is a division, and taking a number of steps is a multiplication because we're doing repeated addition. And so we're free to do that in whatever order. We can move the 3 over under the 4 and say we're taking step sizes of 4/3 every 1 unit. But doing that all the time and using that as a default complicates things when I change the operation from repeated addition to repeated multiplication. So here's why I want us to think in terms of step size and not exclusively in terms of slope. I want to exploit the similarity between a linear function and an exponential function. So if I have a function where the pattern is not repeated addition, if I have a function where the pattern is repeated multiplication instead of addition, I'm going to start with a step size of 1. And I'm going to start with green like I normally do. So let's suppose I start off at 0 and 15. And then 1 unit later, we're at 30. So right now we might be thinking, are we adding 30? That's the first thing we should look at. If we're just looking at 2 points, we should start thinking in terms of addition right away. But then at 2, we jump up to 60. We didn't just add 15 again. And then at 3, we end up at 120. So clearly we're not just doing a pattern of addition. So now we switch to, if it's not a pattern of addition, is it a pattern of multiplication? And that's the case. That's why I picked such obvious multiples of 15. So here is a pattern of repeated multiplication. So to describe what's going on in this function, we multiply by 2. So instead of increase by a fixed amount, we're multiplying by 2 each step. Then we look up at the x's, and each step is a plus 1. Each step is 1 unit. Since our pattern is repeated multiplication, well, let's first write a sentence. We'll say y is equal to 15 when x equals 0. Starts off with the same way we describe a linear function. Where do we start? Then the orange part is, what are we doing? But in this case, we're going to say y is multiplied by 2 every unit. So it starts off the same, but since the repeated operation is not addition, it's multiplication, we say y is multiplied by 2 every 1 unit. But we also want to remember, going way back to the beginning, repeated multiplication is summarized with exponents. When we see repeated multiplication, we should be expecting exponents to show up. Exponents are repeated multiplication. So where we add 4, the repeated operation, the repeated repetition is multiplication. Repeated addition is multiplication. When we can read this equation as start at 17 and add 4 a bunch of times, because we say times x over 3, the repeated operation in an exponential function is going to be exponents. So we'll say y is equal to 15 to start, and we're going to multiply by 2 a bunch of times. But to say multiplying by 2 a bunch of times, we use an exponent. So we'll say 2 to the x. Because repeated multiplication is an exponent. 15 times 2 to the x. 15 times 2 to the 0 is 15 times 1, or 15. 15 times 2 to the first we do 2 to the first, that's 2. 15 times 2 is 30. 15 times 2 squared means multiply 15 by 2 twice. So 2 squared is 4, 15 times 4 is 60. 15 times 2 to the third, 2 to the third is 8, and 15 times 8 is 120. But what it means is 15 times 2, 3 times. 15 times 2 is 30, times 2 is 60, times 2 is 120. So here's an exponential function for what's going on in this pattern of repeated multiplication. Here's what we see in the numbers. Here's how we would describe it in words. And here's how we would describe it with an equation. And it all goes back to how we think about the operations, because that's what we're studying in algebra. How do these operations all fit together in general? I don't want to learn 15 simple tricks to crush your next algebra test, even though most students just want that. I want us to be able to think about what's going on. I want us to be able to see the similarities in the things that we do, even when they get more complicated, like exponential functions. We describe things with exponential functions way more than we do with linear functions anyway. When we talk about how something is growing over time, it's always with percentages, never with fixed amounts. We talk about inflation as a percent per year. We talk about population growth as a percentage per year. We don't talk about inflation as some fixed amount per year. It's based on percentages. And not just percentage points. It's growing by a percent. So, what does this have to do with step size? Let's suppose that our step size, we're multiplying by 2, not every 1 unit, but what if we're multiplying by 2 every 3 units? Let's suppose that x and y looks like this. I'm still going to start off with 0 and 15. And I'm still going to multiply by 2. And so I'll have 15 to 30, then to 60, and then to 120, just like before. So our pattern is still multiplying by 2. But now the step size is not going to be 1. I'm going to make the step size 3. So the thing that's happening to the y is happening every 3 units, not every 1 unit. And our equation, so our sentence is going to reflect that. Easy to incorporate into the sentence. Y is 15 when x is 0, and y is multiplied by 2. Multiplied by 2 every 3 units. So same format that we had before. Where do things start, how things are changing, and how often they're making that change. We only multiply by 2 when we get to a full multiple of 3. So at 3, at 6, and 9. So we're going to adjust the step size in the same way that we do with the linear functions when we wrote them in that weird way. We're going to take the number of steps is going to be x divided by the step size. So the number of steps starts off at 0. A step of 3 is 1, and then 2, and then 3. And then the number of steps is still x divided by the step size, which in this case is 3. So when we go to write the equation, we're going to start off at 15. And then the sentence says, now multiply by 2. And do that every 3 units. So we still indicate, oops, pardon me, pen cap went flying. I've got to rescue it before the dog finds it and eats it. So if we start off with 15 and we multiply by 2, we indicate repeated multiplication with an exponent, so we say to the, but we only do a multiply by 2 when x is a multiple of 3, so we say x divided by the step size, which is 3. In this case, the dividing by 3 has to stay up there with the x. I can't just divide the 2 by 3 because the operation in between is different. It's an exponent. Whereas the operation in between the 2 and the number of steps was multiplication in a linear function. So we're free to move the 3 around as much as we want. But here, I can't move that division across that exponent, not just by dividing anyway. So this is the reason that I care about number of steps and step size. I want us to see the similarity between linear functions and exponential functions. That's the reason that I want us to think about the x over 3. That's why I want to say b plus rise times x over the run, rather than just always sticking the rise over the run and putting that in front of the x. And I want it to go all the way back to the beginning when we first started talking about operations, which is the thing that we're studying in algebra. Any questions? All right. Taking y equals mx plus b and looking at it in this weirdo way is specifically so that we can look at exponential functions and we can see the similarities between the two. We're just trading our pattern of repeated addition for a pattern of repeated multiplication. This is because I don't like the, separating things so much when some things are so similar. All right. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.